Okay, so let's kind of continue with your packet. I'm going to go back to that in a second. Let's look at this. So we're going to be factoring trinomials, 3 terms, and then we're going to be factoring a difference of 2 squares. Remember, a difference for 2 squares, you're always going to have a 0 pair because you don't have a middle term. Your bx is actually 0. So what are numbers that are a 0 pair that multiply to make a negative 49? Positive 7 and negative 7, of course. And I'm sure some of you guys already have that factor written down. So again, pretty low level, c minus 7, c plus 7. However, what are those? We know what those are. What is that pair called where the middle sign is different? Starts with a C. Conjugate. Very good. All difference of squares, y'all, are conjugates. All of them. So this word certainly has a place with factoring. Conjugates. Number 5, I'm confused because 3 is not a perfect square. Yeah, that's greatest common factor. So when you do factor out your greatest common factor, please do not forget to put that greatest common factor at the end of your complete factored form. Do you have any questions on 3 and 5? Any questions on 3 and 5? I can't hear. Can you please say that?
You didn't do an x plus 5. You just did.
Thank you. Thank you. My conjugates were not correct. Make sure you have x plus 5 and x minus 5. Okay, so let me go back to some stuff that's not in your packet. First of all, things are going to get amped up a little bit. And I don't know if you're kind of looking down at problem 7, problem 4. You got some crazy looking exponents there. Not a big deal. Exponents are not going to be a big deal as long as you remember all exponents that are even are perfect squares. So v to the 200, that's a perfect square. C to the 124, S to that thing, as long as it's even, it's a perfect square. Why? Because it's what? Yes, kind of, yes. I know what you mean.
It's like how the 4 makes it 1.
The exponent. Can I break up those V's into 2 separate groups evenly? What would the 2 groups of those V's be? V to the 100, V to the 100. So if I had V to the 100 and V to the 100, remember when you multiply exponents with the same base, you add the exponents. That would give me the area of a perfect square. This would give me the area of a perfect square. That other one, which I'm not even going to embarrass myself to try to cut that in half right now. If that's cut in half, that would give me a perfect square. Speaking of perfect squares, after I cut it in half, could I keep going with this right here? Is 62 even? Then I can keep going, which is foreshadowing for what we're going to do in a minute. And that 3 to the 31 times 3 to the 31. Could I keep going from there? Why not? It's odd. I can't cut it in half evenly as a whole positive number. Exponent. All right. So things are going to get crazy with exponents. Speaking of exponents, they're going to be a little crazy in trinomials also. However, that needs to read 22x plus 22. We're actually going to factor this right now. Let's go ahead and read what it says. A trinomial may be factorable if The middle term's exponent is half of the highest degree term's exponents. In other words, don't look at that right now. Pretend we had a regular baby quadratic and we were going to factor this. This is what this stuff means. Is that exponent half of that one? Yeah, that's a 1. Isn't 1 half of 2? Of course. So let's kind of analyze what is given to us and see if it is indeed going to be factorable. So what I'm going to do is I'm going to factor the exponents. So this is going to be x. I'm going to factor a 44 out. And I get 44 times x plus 1. So what that means is x is being raised to 44x plus 1. That's what that means. Let's take a look at the next term. I can factor out a 22. Do you think that I can keep going on this? Is 22 half of 44?
Yeah.
Then we're going to be able to keep going as long as there's factors of negative 15 that make it positive 2. Is there?
Yeah.
I need to make a negative 15.
Three.
A negative 3 and what?
Five.
Yes. Okay, so let's factor this because remember it's fun to factor. So this is going to be x. Remember you cut the exponent's number in half. If there's 44 x plus 1s, then this is 22 x plus 1s. Plus 5. X to the 22 x plus 1s minus 3. That's it. It's factored. Let's box that in. It's all about being able to cut it in half, is what it boils down to. You got to be able to cut the exponents in half. Any questions on that?
Did you not put it down further?
So when I factored a trinomial, I got 2 binomials, correct? Only if that was a difference of 2 squares. If that minus 3 would have been a minus 4, we would have to keep going because that's even. But it's not. So we're good with how it is. If I have 4 m's, there's 4 m's laying on the floor. Can I put them in 2 equal groups?
Yeah.
What are they?
Yeah.
Yes. All right. So it's going to be x to the 2m minus y to the 2m. And then the other one's going to be an x to the 2m plus a y to the 2m. Man, did I even say thank you? I don't even think I said thank you. I need to go tell her thank you. I was just excited. All right. So, 2 things. You can never, ever factor a sum of 2 perfect squares. That's always prime. Because we are factoring with real numbers only. We're not pulling out eyes and doing all that weird imaginary stuff. Let me show you why it's prime. You can write this down if you want. I'm just going to show you a little side example. Up to you. I don't care. You'll get this as soon as I show you. The reason why you cannot factor a sum of 2 cubes is or 2 squares. Think about what happens if I try to solve that. Let's put it equal to 0. So you push a 25 over. What do you get for your answer? You get some eyes, right? That's why it's always prime. The sum of two squares is always prime because we're factoring real numbers only. The sum, the sum, the sum. That's not a sum. That's a minus sign. Are these even?
Yes.
Oh, then I get to keep going. I'm so excited. That's still a difference of two squares. We have to keep going here. So let's break those m's up. They're going to break up to just single m's now. X to the m minus y to the m times x to the out. Box this in. Do you guys have any questions on that? Oh, I'm sorry. Did you see that? That was my trick. Did you want to see it again? These are my awesome animations, my awesome graphics. Oh, speaking of trick or treating, this right here, what number is this, guys? Number 9. That's a teacher gotcha. Yes, always prime. So just write prime. You're not going to fall for any of Miss Harrington's tricks. The sum of two squares is always prime. I just showed you why. Don't fall for it. All right, y'all, let's see what's next. Yes, number 7. So now we're going to go to number 7. All right. I have even exponents. I have a minus sign. I have perfect squares, and I have only 2 terms. Is this factorable? All right, so the root of 16 is 4. How many A's get dumped into each of those? Yeah. I'll go ahead and write the plus first and then the minus. Y'all, what's going to get tagged at the end? 9 to the B2, yes. 9 to the B squared. So October 28, 1132 will be the date that you forever have to check to see if you can keep going. You always have to check from here on out to see if you can keep going.
Yes.
Thank you. So I know this is prime because it's a plus sign. I'm not falling for any teacher tricks. But that other one is a difference of 2 squares. That's 2a minus 3b times 2a plus 3b. Guys, how many A's did we start out with? How many A's were in the original problem?
4.
And if you notice, they're still here. 1, 2, 3, 4. They're still there. They've just been all factored out. Same for your B's. 1, 2, 3, 4. So it's all still there.
Miss Harrison,
Yes.
does it matter where the positive binomial goes? Like at
Nope.
the beginning or
Good
the-
question. It does not matter the order at all. Remember, 5 times 3 is the same thing as 3 times 5. Order does not matter at all on this.